So fiat lux, let there be light. So here we have a procedural solar system. Each planet obeys Kepler's laws, and there's different scale, different materials, and different angles of inclination, eccentricity, specific angular momentum, and some of the other orbital parameters are different for each one as well. So let's start a geometry nodes setup. I'm going to keep the timeline in the middle, and we're going to use this simulation zone that's new in Blender 3.6. So I need some values for the inputs. There's a bunch of variables here. And these are all going to be the inputs to the simulation. So there's nu naught, E, which is eccentricity, P, which is the simulatus rectum, H is the specific angular momentum, and dt is the time increment. So with that, we're able to, knowing the angle and the radius is, this r is a distance from this focal point to a point on the ellipse, so it sweeps across the ellipse. The angle nu is swept, so it's 360 through each orbit, and these are the equations that describe the area. And Kepler's law says that equal areas are swept in equal times for a body in elliptical orbit. And this is the equation for r in terms of the other parameters, and I'm kind of jumping here. I'll show this again at the end. The eccentricity is a ratio of the distances between the focal points and then the major axis there. So all those are inputs, and first I'm going to set up some of these equations. There's a cosine and there's a sine function, and these need to be multiplied by e. The cosine needs to be multiplied by e. Remember, the new cosine e is in the denominator of the function for r. So 1 plus e cosine nu, and then that's in the denominator, and the numerator is p, and that'll give you r, so I'm changing it to r here. And then with that, I'm going to need r squared for the calculation of the delta nu. And then to calculate the delta nu, I need the dt times h, and then that's divided by r squared. And this cosine and sine, those both need to be multiplied by r, and that'll give us the x and y locations of the planet as it goes around. So that's going to go into the x and y, the cosine into the x, and the sine into the y. And then that's going to go into a set position node. So here I'm connecting it to the set position node, and then I'm using the node wrangler shortcut, which is shift and then right mouse slash across to make a new node and reposition that. And then what I need to do is take I'm going to change this and note that this is the delta nu, and then the nu that's going into the next iteration of this whole thing is going to be delta nu plus nu. So here I'm taking nu and I'm adding the delta nu, and then that goes into the nu naught, that's the output, so that's going to be used in the next iteration of this loop. And then I'm using the right mouse slash across with holding the shift to make those extra nodes. And then I'm connecting the parameters for eccentricity, simulatus rectum, the specific angular momentum, and then the delta t. And then I'm using that shortcut again to move these all down to the bottom, so things are a little clearer. And then for new, I'm starting it off at pi, and then eccentricity, I'm going to use 0.6, p is 20, h is 500, and delta t is 0.1. And then I need something for this to act on, so I have a curved line, and I'm going to use that to go into instance on points, and then for the instance I'm going to make a icosphere there. And I'm going to put that on the one on the y for the the end point, and make z 0. Z and x are both 0. And so you can see I have something moving there. And if you watch it, you can see as it gets closer to that focal point that's at the origin, it moves a little faster. So you can see it's kind of behaving the Kepler laws. But you can see that there's two instances there, and they're both getting the same information. So there's actually two icospheres that are on top of each other. But what I want to do is kind of give it some variety. So I'm going to put in a resample curve and then adjust the length in order to get 3 instances. And up here I've changed the upper right to the spreadsheet, so you can see if I click on the instances, you can see there's 3 instances. And then I'm going to put a random value in for p, and here I'm just kind of playing around with those numbers, and I'll adjust them as we go through this to get something that I like. And you can adjust those numbers for the max min, and then also the seed, which will pick different ones. And you need to make sure that you make the attribute an instance attribute, and then you can see I get different random values for each instance. And here I'm gonna move them in closer, and here I have 3 of them kind of orbiting around. One's really slow and far away, and then the other 2 are closer. And you can see they all have different distances for their orbit. And I'm going to adjust some of those other ones, the eccentricity and the angular velocity. I'm going to eventually put random values in for those nodes as well. For those variables as well, I mean. So I want to show you what's happening here. So I'm going to put this store named attribute, and here I'm reading in this eccentricity value. And then I'm going to do the same for p and h, the simulatus rectum, which is a geometrical number there, and then the h, which is the specific angular momentum. And here you see the position is changing, but the e is kind of decided at the beginning. And you can see the eccentricities are all set, and they're all somewhere between 0 and 1, and for some reason they're very high for this. So what I want to do is also add the store named attribute for p, and then I'll do the same for h later, and you can see that those numbers are set at the beginning and then they don't change. So here I've copied over that random value and adjusted the values. The eccentricity, if it's 0, it's a circular orbit. If it's 1, it's elliptical, and above 1 it should be either hyperbolic or parabola. And then h, the angular momentum, I'm changing that too. So they all have the same focal point, and they all kind of have the same the point of closest approach to the center there. The focal point at the origin is the same for all of them. I could have changed it so that there's some angle that's different in Z for each of them, but I didn't do that. It looks pretty good kind of as it is. So I take the combined X and Y that I'm calculating, and what I want to do is give each orbit a different angle. So I have a random value, and I'm kind of playing around with the seed and what the min and max is. The min is going to be 0, so it's a 0 angle, and that's a sine multiplied by R. And that'll give us a different angle with respect to the XY plane for each of the orbits, for each of the planets that are orbiting there. So I put a shade smooth on each of the icospheres, and then I'm playing around with the random values, and what I want to do is adjust the scale of each of these icospheres. So that's going to go into that instance on points. And you can see here, each is a different scale. So I'm just adding a little variety to it. And here I'm going to play around with the materials on each of these, and you can see down there in the lower right, it shows me how many faces there are on each of those objects, the instances. And so when I realize those instances before it goes into the output, I can set a material, and then what I'm going to do is I'm going to put a different material on each of them, and here I'm going to make the materials, and here's one. I'm going to make it a little red, put some noise in there, and put it through a color ramp. And here I'm using the generated, and if I remember, that didn't work out so well. I think the normal is what I eventually used for all the texture coordinates, and that seemed to work the best for me. I think the generated, as the planet swept around, the texture was changing, but the normal didn't. So here I'm adding some orange and red colors and adding distortion, so it kind of looks like, maybe Jupiter or something like that, a gas giant. And then I have a couple more, and this one I used a Musgrave and tried to make it something that's maybe kind of Earth-like, a lot of water and beaches and maybe green for the land. And I put this through a bump node to try and make it stand out a little bit more. It's so small you really don't notice it, but just playing around. And then the other one, I wanted to make it like one of the ice planets, like the outer ones, Uranus. And so I'm using the index input and using the less than and greater thans to set up numbering, and the numbering is going to be the number of faces on each of these. And I'm going to try and set those up so that it selects a certain face index for each of those materials. And that's going to go into the selection on each of the materials. And as we kind of zoom forward and kind of skip a lot of the tedious setup here, you can see it's either greater than or less than, and you're picking a range, and that goes into a Boolean and then that goes into the selection, and that allows you to pick a range of index values for those specific materials. So here I've done it this is the third one, so I'm adjusting these. And then that goes into the last selection. And I had to play around with these until I got the behavior that I wanted. So here I have it set up, and each of the planets has its own material now. And there you go. Now the sun, I didn't want to do it procedurally because it just kind of sits there at the center and does nothing. So what I did there is I just added another icosphere and made it shade smooth, and then added an emission texture to it, an emission material to it, and here I'm doing that. And I cranked up the emission, and it really didn't give me the brightness that I wanted, and so I added a couple of lights there and really cranked up the intensity of them, and you can kind of see that in the animation I had at the beginning and at the end of this. You can see it's a little, even though it's the sun is an emission body, you can see the top and bottom are a little brighter than the rest, and that's because I had a couple of lights kind of set up either above or below it. So here it is, 3 bodies going around. They each have their own parameters. Now the background I didn't like too much, so I changed the world, and I went to the background, and I, using the Node Wrangler shortcut, the Command T to generate the texture coordinate, the mapping, and then it creates an image texture. And if you do a Shift S while that image texture is selected, you can choose through the menus, and I chose to change it to a noise texture, and then adjusted the noise texture through a color ramp, and that I'm using as the background, and adjusted the brightness. So when that works, it kind of looks like a bunch of stars in the background. And here I am putting those extra lights in there and kind of cranking up their intensity so you could see the outer planets when everything else is dark. So here's kind of the theory. Kepler, he said the motion for the planets are elliptical, equal areas are swept out in equal times, the period squared is proportional to r cubed, and then Newton came up with the law of universal gravity, and here I'm kind of going through what that means in terms of the force between the two. The acceleration, the r double dot, is the acceleration vector between the large body, big M, and the small body, small m. And if you assume that big M plus small m is about equal to big M, you come up with that relationship there. And through conservation of angular momentum, if you go through that, you can see that that h is a constant value for each orbit, and then the trajectory equation, you can go through the derivation here. You can find it in a lot of books, and you can probably find it on Wikipedia online. But I'm just kind of writing this out. I kind of wrote it all out, and it was kind of took a long time for me to write out the whole thing, so I sort of fast forwarded through a lot of it. And so here it comes, all sped up. And you can stop this where you want. And these are the basic equations, the period, and that's where it's all derived for the trajectory equation. So this is the derivation of r, the equation we used for r, and then showing where the period comes from. That's just a geometry there, and those are the equations for the ellipse, just if you're interested. So that's about it. If you like this, I know the end here is kind of fast and furious. You could doubt too many people or care about the details of the math, but that's it. If you like it, please click like, subscribe, and I'll see you in the next one. Thanks.